in this class, we're going to finish this effect. We're almost there. We're just missing to add a little bit more of variation and just tweak a bit more these parameters, just so that we can get our final look. And then we're just going to upres. But the first thing I want to do is I want to have a look at our popnet. Specifically, I care about the bounce and the friction. So right now, the particles are bouncing and it's not very realistic. You can see if I stay here, the amount these particles are bouncing isn't realistic at all. I'd also like to add an extra layer of variation. So if you recall from a previous lesson, I talked about some of the attributes that the pop solver recognizes, and we're going to have a look at 3 of them. So one of them is going to be called bounce with lowercase, like it says, it literally is the parameter name. Another one is friction, and the third one will be mass. The advantage of doing that as an attribute instead of a parameter is that right now if I change the bounce or the friction, it's going to change it for every single point. And the thing is, all the points are either going to bounce more or less, or slide more and slide less. What I would like to have is some variation where some points bounce more and some others bounce less, and so on. And I'm going to be adding mass because I want to add a bit of drag. Right now the only force that we have is gravity, and everything right now is set to ignore mass. Now if we create some mass, that's going to allow us to have this pop force affect the particles with more mass differently than it does the ones with less mass. And same when we add force. The same when we add the drag, which is going to be like air resistance. So let's go ahead, and I'm going to go after our set velocity magnitude. I'm going to create a new point pop, and I'm going to call it set mass, bounce, and friction. So let's start with the most obvious one. Let's start with bounce. So by default, if we use any attribute, by the way, it's going to completely override what we're having here. So this isn't going to have any effect anymore. But just so we know what bounce does, if I set this to 2, for example, so you will see our particles are going to bounce a lot. We can see the ones from the beginning actually. We can see how much they're bouncing, and we're going to go the opposite way, set it to 0.1, and this way they're not going to bounce at all. Right? So we have to find a value in between, and we have to find like a minimum and a maximum value. So let's start with our bounce. First thing I'm going to do is select our point number, and I'm going to change it into a float. And then we're going to go into a random. And let's turn off clamp position to integer. And let's create a ramp for it so we can distribute it. And there's one thing, is I'm going to use this for bounce and the mass. So I'm going to call this bounce mass distribution. And then I'm going to fit it. And finally we export it. And it's going to be called bounce. Okay. Let's promote the minimum and the maximum. So this is going to be our min bounce. And then this is going to be our max bounce. Okay. Let's go up. And let's set the ramp. So by default, I want a lot of the pieces to bounce very little, actually. So something like that. So with a curve like this, most of the points are going to bounce little. So let's see. Let's set our minimum bounce to 0.2. And let's set the max to 0.5, for example. Let's turn off this grid. And let's have a look at the result. One thing that's bothering me is that the SDF is taking a while to calculate. And I've mentioned before how important it is to iterate fast. So we're going to have a look at how to make that faster. Okay, and it looks like it's not bouncing much. So our values are way too low. But before we do anything, I'm going to fix our ground. So As you can see, we're bringing in the whole ground, and we're only using a small part of it. So I'm going to bring it in manually. Let's see, it's under environment, road, out. Let's hide other objects for now. Okay, and I'm going to template the hits, just so I know. For some reason it's only showing those. Okay, there we go. Just had to into wireframe mode, and I'm just going to select over here these primitives, something like that. Hit delete, and it's not selecting them. No, it's because it's packed. So let's convert it. Okay, and now we can select it, hit delete, delete not selected. Okay, so this is now going to be our new ground. Not sure why it's showing. Oh, we have the points on. So let's see. Let's call this our null. Let's call it ground. And I'm going to connect it into the first input. And in here, instead of telling it that we want it from the subpath, we can use this expression. So I'm going to use a backtick, and I'm going to tell it op input path. And what this expression allows you to do is you can give it a path to an input. In this case, I want the input of the .NET. So for that, I'm going to put 2 dots. So one point means the parent of this node, and another one means the parent of that node. That's the .NET. And then comma, you will specify the index of the input. So in that case, it's starting from 0. So in our case, it's 1. And if you middle mouse click here, you'll see it evaluates to that. So that's an easy way of not having to change the path. Basically, anything that goes into the first input is going to go into here. Okay, and now, if we show the collision guide, it should be faster to calculate. Like we can probably go to 250. Yeah. And we'll still get a good representation, maybe even 200. And that's going to be a lot faster. Okay. Let's see how much faster it is. That's great. Okay, now we can start working with our bounds. So let's go here. Let's look at the final results. We can show again all the objects. And let's go into our bounds. Let's hit play again. And it seems, it's strange that nothing is bouncing at all. Let's see, I'm going to try with 2. Okay, there we go. Now they're bouncing. So I think I'm going to try to do the opposite. So I'm going to keep this curve. I like the distribution for the mass. So I want most of the points to be to actually have a small mass, so they're going to be small, but I want to do the opposite for the bound. So if this is our mass, so actually let me show you what I mean. I'm going to go here and also fit this again, and this time I'm going to call it our minimum mass and our maximum mass. So min mass, this is our max mass, and let's save it as mass. So this is the curve I also want for my mass. So basically I want most of the particles, they're going to be small. You can think of this like p-scale. In fact, we're going to be remapping our mass to p-scale later on, but I want most of the points to be small and a few of them to be big, right? It's a distribution we talked about before. So let's see, for the mass, I normally always leave this in 0.75 and 1.25. So I have like basically a 25% variation. It either goes, it's slightly smaller or slightly bigger. I don't like changing that too much, but you'll see. It will just add a very, very small difference. But anyways, there's something I like to do with the bounce, and that is I want to invert it, because sometimes smaller objects tend to bounce a lot more than big ones. So what we can do for that is actually come here and add a complement. And that is going to do basically 1 minus that. It's going to invert our curve. So now it's going to look something like that if I were to draw it. So that means that now most of our points should bounce a lot more. So we can see now we're seeing a little bit of bounce. So let's go back here. Let's see, let's change it a bit more. Let's just say maybe 0.6 and 0.3. Okay, and to see this properly also, we need to start adding friction. You can see right now, they're all freezing and bouncing in the same place. But I kind of like the bounce so far. Like some of them are bouncing a bit, some of them aren't. You can see they're all stopped at different times. Before they were all stopping at the same time. So actually, let's go ahead and add the friction as well. So let's go in here. And I'm going to create another random. But in this case, I want to have a different seed. I don't want this to have the same random value. So I'm just going to say add constant. I will just add a random number like 55.34. So now we get a random of that value and we can have a ramp. You can set it to be spline ramp, friction, distribution, and then we're going to fit it into our min friction and max friction. There we go. And then let's export this to friction. Okay, and in this case, let's see, I want to have almost all the points with a lot of friction. So that means that they will slide very little. So something like that. And let's see, we can go with a value like maybe, let's see, 0.05 and 0.2 maybe. So let's see, this should let them slide a lot more. Let's hit play. And it might be too much, so I'm going to lower it. I want them to keep sliding, you know, like, there we go. Maybe even less here. Okay, that's starting to look more realistic. So you can see how now our particles are actually starting to behave. I think they might be bouncing a bit too much, so I'm going to lower the bounce to maybe 0.05 and maybe to 0.2. Okay, that's looking a lot more realistic. Cool. The last thing I'd like to add is, if we go here, I mentioned the pop drag. And I'm going to tell it to not ignore the mass. And let's see, I'm going to set the air resistance to be something pretty small, so like 0.01. That is going to add a slightly more variation when the points are falling. Okay, and let's have a look at from the camera. Cool. Now I think we're ready to start instancing our geometry. So for that, let's go back to our attribute delete. And instead of having this, I think sometimes it's easier to just have a clean. And we can turn on here. We don't want to remove all the points. We just want to remove some attributes and some groups. So let's see what groups we have. There's just that group, so yeah, we definitely don't need it. And it's very important to clean up your geometry after a DOP simulation, especially with particles, because it ends up adding, as you can see, we have 20 point attributes, 6 detail attributes, 1 primitive attribute. We have a lot of things. Now, whenever you save this on disk, this is all going to take up extra space. So you always want to make sure you get rid of all the things you don't want. So for example, I don't need anything. We don't need H or air resist. Really, the only things we want are bullet impact. So I will say delete everything except bullet impact. And I have a typo there. There we go. So bullet impact. Then we have centroid. Okay, we might need it. I'll keep it just in case. Then we have our distance. I'm not sure if we need it. Let's see. Let's hit frame. That one can be useful. And then our ID, of course. That one's always very important to have. And then our mass as well, because we're going to want to use that for our p-scale. And then source, well, and the velocity, of course, how fast it's moving. But you know what, I'm just going to remove the centroid. I don't think we need it. I think that will do. Okay, and now I'm going to rename our mass to p-scale. And I'm going to go into a point bob, and let's actually set a proper p-scale value now. So if we bind the p-scale and we fit it, and we set it before to 0.75 and 1.25. Now we can give it a new value. So mean p-scale, and this is going to be our maximum p-scale. I'm not using a ramp because we already used a ramp in the mass. So remember, we're renaming our mass to be the p-scale, and our mass is already distributed with that exponential ramp, exponential curve. And now we can save this back to our our p-scale. And let's see, we can go 0.1, 0.2. And now I'm going to just do copy to points. And I'm going to copy a sphere. Set it to polygon. You can connect it. And you'll see by default it's quite big. So I'm just going to make it smaller in here. Let's see, let's turn off our show guide geometry. Okay, and I'm going to add, so let's zoom in here, just to make a debris. I'm going to add another point jitter, and I can set this to, for example, 0.01, and let's see, maybe a bit more. Yeah, something like that. And that's going to be our debris. Believe it or not, just something like that is good enough in this case. We're going to have a look at more complicated ways of instancing geometry and different geometry. And since it's all the same, we can tell it to packet an instance. And let's see, we can change now our p-scale. I'm going to go, let's see, a lot bigger. And I think I have to go smaller in this one. 0.05 maybe. I'll change the scale here as well. Maybe that one was too much. Let's see, 1. There we go. Now we can see some pieces. I'm going to give them a color, just so we can tell them apart from the background. So let's see, something like brown. Okay. And let's have a look at what it looks like now. Okay, and that's looking a lot better. You can see it's no longer playing at real time, so we'll probably have to do a flipbook. But the most obvious thing right now is that we're missing some particles, so let's go ahead and do some cleanup actually on this setup. So there's one thing that I forgot that I changed, and that is when I was showing the example with the point order, I ended up leaving this at 2, I believe, instead of 0.2. So yeah, my bad. I'm going to fix that. Let's see. I think all this is fine. Okay, here we go, the scatter. So right now we have 12,000 points. We're probably going to go, let's see, times 8. 100,000 points. Let's see what that is looking like. And I'd like to add another check after this. And the thing is, when we add our attribute noise, some of our points might end up going under the ground. So it's always a good idea to have a final ray against the ground. Something like that. Let's move all this down as well. Okay, let's visualize the color. Let's go back to the first frame. And I'm going to create a flipbook. Now, when you make a flipbook, it's important that you go to the size and you turn off resolution. If not, it's not going to use the camera's resolution. Let's see, I'll hit play. And looking at it now, we can probably add a lot more points. Also, we can make it smaller. I think the debris now are looking way too big. But it's starting to look pretty cool. It does look like bullet impacts. All right, I'm going to close this. Let's go back. And let's see, we can make this a bit smaller in the P scale, for example. So maybe we can go to, well, the things I like to keep this because this is the distribution, right? We go from 0.1 and 0.7. We can make it slightly smaller here. Let's see, let's look at one of these frames. I think the point jitter doesn't help. There we go. Let's see, this might be a bit too dark. Let's make them a bit lighter. Okay, and we probably will end up needing even more of these particles. And let's see, let's have a look now at our velocities. I'm going to go back over this and start adjusting. So let's visualize this. So this is just our direction. So let's say I want to add a bit more variance maybe. So let's say I'm going to increase. Let's increase the frequency a little bit. I want to have like even more random directions. So let's see, even a bit more roughness, for example. There we go. That's going to add a bit more variation. And let's see what else we have here. So I think our minimum noise, I think that's fine. If anything, we can add a tiny bit more, something like that. Let's see our magnitude. Let's try sometimes more contrast. Looks nice. In this case, it looks just like it's not doing much. Let's see, is it? Yeah, I guess after a certain point, it doesn't really do anything. So let's just set it back to 4. I'm sorry, what was the value? 3.8. See, roughness, noise amount. Maybe we can have a tiny bit more of noise. Okay. I think that's pretty much it. Sometimes what I like to do is, let's see, when we have a look at this in pops, I like to sometimes add a bit more variation in here. So let's see how this looks. So if you feel like, you need a little bit more variation, you can set to add to inherited velocity. I'll set back to what it was, and you can add something very small, like just 0.01. It's going to add like just very small directions, very small changes in your velocity. That sometimes helps. And also, if you feel they're going way too high and it's way too fast, you could lower it, for example, 0.9. Let's see from the camera. So they might be going a bit. Let's see, let's go to 1.2. Let's see how high they go. Yeah, actually, these are going pretty high for bullet impact. So you can see there's a huge difference just between 1.2 and, for example, 0.9. Look how high they get. And let's see now with 0.9. Right, it's a lot lower. I think that might work. Even less, like you could consider going with even less height. But this gives it you don't want to go too low, because if not, it will lose a lot of that impact and that just the force it gets on the impact. And I think that's pretty much it. Let's go back to the color. Let's run it again. Let's hit play. Cool. I think we need a lot more particles, but before we do that, that's going to be our final touch because it's still pretty fast to iterate. I want to show you something, and that is if we zoom into any of these impacts, you're going to see that everything looks exactly the same. And so far, everything we have done is in relation to how the particles move, how they bounce, how they slide. But we have to remember that at the end of the process, we're going to be copying geometry onto every point. So there's one very important aspect that we're missing in this simulation, and that is the spin of the particle. Obviously, with a point, you can't really tell if it's spinning or not. That's why it never really bothered us before. And by default, there's not going to be any spin added to the points, as you can see. This is the final thing that we need to make our simulation look better. So let's have a look at how we can add this spin and how we can visualize it in DOPS. So in order to get our particles to spin, we need two attributes. One of them is the orient, and the other one is W, which stands for angular velocity. The orient attribute describes the orientation, and W the angular velocity. So orient is a quaternion, which you can think of as a vector with 4 dimensions. We won't get into the details of what exactly a quaternion is, and honestly, you don't really need to know much about it since Houdini always takes care of the math for us. All you have to know is that quaternions are a very accurate way of describing rotations. Euler rotations, which is the one we're used to when we rotate things. So when we do, like, let's say I create a box and I create a transform. Let's see. I didn't connect it. So this, right, the three handles, those are the Euler rotations. So it's very handy for us humans to rotate person in the viewport. But actually, for the computer, it's not the best way of describing rotations. They are actually inaccurate, and you can have problems like gimbal lock. The nice things about quaternions is that they don't have any of these issues, and they're a lot more efficient for the computer to handle. All you need to know is that a quaternion is a more accurate way of representing rotations. So let's have a look at what this looks like. I'm going to create over here a sphere, and I'm going to hide everything. And let's just scatter a few points. Let's say like 2 points. Let's visualize them. There they are. And the easiest way to create an orient attribute is to just go and create a attribute randomize. And we can tell it here we want an orient. Can tell it over here it's going to be direction or orientation, and it's going to have 4 dimensions. So you can see 0, 1, 2, and 3. And the best way to see what this is looking like is if we press D and we create a new visualizer for it. We call it orient. I'm going to set the style to be axis, and this is going to give us 3 axes. That's the easiest way to visualize this. Set it to 0.2. and you'll see it will make sense. So now if we turn on our visualizers, there we go. You can actually see this looks exactly like our origin. What is it called? Our origin gnomon. So basically you have the 3 axes, but you have them in every particle, and this describes how that particle is oriented, right? That's our up, C-axis, that's the front, and then that's the X, that's the side vector. So if we copy anything onto it, like let's say a pig head, and we copy 2 points, see, we connect these 2 things. Let's make it a lot smaller. You can see we very easily change the orientation of these pigs, right? If we bypass this, they're going to be the same. That's what's happening with our particles right now. Right now they're all different. Okay, so I'm going to copy this and let's paste it over here in our, like after we set our mass. Let's add some space for us. Okay, so I'm going to call this create orient. Now this, if we look at the result, is going to look a lot better. You'll see that we're not going to get those particles looking exactly the same anymore. So let's see, let's go here. Actually, it looks like, is it using it? Let's see, I'm going to reset our simulation cache. Let's have it cook again. And it looks like it doesn't like it. So let's see, let's go to our options. And let's change the global seed. Reset it. And for some reason, they all still look the same. But a good way to debug this is we can turn on our axis in here. Probably should make it a lot smaller now. So let's see, 0.02. There we go. Let's turn off our velocity. And they are different actually. Oh, so you know what this probably is? Yeah, that's our clean. So we were deleting it. Okay. There we go. Let's have a look at it now. There we go. So now you'll see they're all different. And that's what I meant before when I said that even though you're copying the same geometry, the fact that they all are differently oriented and you have motion blur and they're going to be spinning now, there's no way you're going to tell at that distance that they're the same shape. And you can get away with something so simple as a sphere and a point jitter. Okay, but still, if we look at one of these, and the best way to look at this is, I'm just going to blast by ID. So I'll say ID is equal to 1. Points, delete non-selected. So if we look at this piece, you will see it's not actually, where did it go? It's not actually spinning, right? So we changed the orientation. What we didn't change was the way it's spinning. So let's go back up. And for that, we need a second attribute. So I'm going to demonstrate it with our sphere example on our 2 points. And that is the angular velocity. So the angular velocity is represented by the W attribute. And this is a vector attribute where the direction describes the axis where the particle spins around, and the magnitude of the vector is the speed at which it spins. So we can go ahead and create a random. Let's see, attribute randomize is going to be direction or orientation, and we're going to call it W. Now this is going to give us a normalized vector, and we can actually create a visualizer for it as well. So W, this one can be a vector, 0.2. See if we can make it red. Let's turn off our orient. And basically this means that the particle is going to rotate around that axis, but they're all unit vectors. So what we can do is create a point pop. And what we can do is we can bind our W attribute. So it's going to be a vector. And then we can create a random value here. A ramp. We're going to call it our angular speed distribution, and it's going to be a float. And then we can fit this from 0 to 1 to 2 different values. But one thing to know about the angular velocity, and that is that it's set in radians. I guess you have either degrees or radians, just a different way of expressing an angle. We don't have to care about it. We can just write in degrees, and we can write degrees to radians. Have Houdini convert it for us and do all the hard work. So like that. And finally, we can just multiply, since these are vectors, right? This is our normalized direction. This is our magnitude. And then this is our new vector. So W. Okay, and I'm going to call this our minimum angular velocity. And this will be our maximum angular velocity. Okay, we can go back up. Let's change this ramp. And like always, we can just have very few pieces spinning very fast and a lot of pieces spinning slow and a lot of them spinning really fast. And we can tell it, this is gonna be in degrees. So this is in degrees per seconds, by the way. So we can have it spin, for example, do 1 turn in 1 second. That's the smallest one. And we can say, 600. So if you want a full spin, you could do that. 720. So it means the maximum, like these points are going to be spinning twice every second. And we can actually copy this. And let's go back here. And let's paste it after our orient. Okay. Let's hit play, and you'll see by default you don't see anything. The only thing you'll see is if we look at our angular velocity. Can make this a lot smaller. The angular velocity isn't going to change, but the orient now will. You'll see now these particles are rotating. They weren't before. And now they're going to be spinning. It's easier to see if we go back to our blast, to this guy. There we go. So let's have a look at the orient here. So you can see there our orient is changing. So let's go to the end, and we can see it's still spinning. So it might be a bit slow. We can end up increasing it here. We can say times 2 times 2. Now it's going to spin twice as fast. Right, and then again we can say the maximum can be times 4. And some of these particles are going to spin really, really fast. And I think with times 2, it's good enough. Now you'll see there's a problem. And I don't know if you noticed already, but this particle is already on the ground and it's still spinning. Right? So it shouldn't be spinning anymore. And that's because the way we're adding our angular velocity, we're kind of, well, since we're dealing with particles, we don't have like an RVD where we can have, the object actually roll and slow down. We have to slow down everything ourselves. So for that, I'm going to create a pop drag spin. So the pop drag is going to affect the B attribute. The pop drag spin affects the W attribute. So here under spin resistance, that again is same as the drag, is how much it should stop them while spinning. We don't really want them to slow down while they're flying. It should be like really, really small, the change. What I want to do is I'm going to use expressions here, Vex expressions, and we're going to say if a particle is on the ground, basically, so if it's below a certain threshold, and if it's not moving, then we're going to increase the spin resistance by, we're going to set it to 10 or 100, for example. So the way you do that is we're going to say if the length of the velocity. So remember, length of the velocity, that gives us our speed. So if the speed is less than, for example, 0.1, that's pretty small. And if our position in y is less than also 0.1, then this attribute is called spin resist. So we can say spin resist is equal to 10. Otherwise, our spin resist will be the way it is. We'll just grab from this parameter. So we'll say spin resist is equal to spin resist. Okay, and now if we visualize this, we should see that the particles stop spinning once they stop, right? Once they reach to an end, and once they stop moving, there's no more rotation. Cool, so we don't have any more crazy spinning there, but when they do shoot out, they are spinning. Great, so I think that's it. The only thing we have to do is increase our scatter. So let's see, I'm going to go, let's see, times 2. So you should get 200,000, maybe 2.5. 250,000. Let's see what this gives us. So I'm going to save it. Let's go into the scene view, to the camera view. Let's show all. And let's do a flipbook. Alright, so this is done. So let's hit play and see how it looks. Awesome, so I think we have a pretty good first version. And now that we have our effect done, the nice thing is that we've been over all the major concepts, such as orientation, velocity, angular velocity. We've been over bounce, friction, p-scale, source variation. The nice thing is that in all the next effects that we're going to be doing, we're going to be reusing this setup, just changing it slightly, tweaking the parameters, but those are all the building blocks to build 90% of all the impact-based particle simulations you're ever going to do. So in the next lesson, we're going to go ahead and reuse this setup and apply it to the first shot and to the third shot.